In this video, I'm going to go over the formulas that are used in a factorial ANOVA and how we make decisions. So we're going to overview what are called the stage 2 calculations, which are basically mean squares and F-scores. You're familiar with these. So when we are doing a factorial ANOVA, we actually have 4 mean squares that we need to figure out. We need to figure out the mean squares for factor A, the mean squares for factor B, the mean squares for the interaction, but we also need to figure out the mean scores within treatment for the whole study. So as a reminder, you're not required to calculate the sums of squares in this lesson. So take a breath and just know that I'm going to give you the sums of squares and you're going to divide them by the degrees of freedom that you have already figured out how to do, right? So we're going to find the mean squares for factor A, mean squares for factor B, mean squares for the interaction, and the mean scores for within treatment. We find the mean scores for within treatment because that's going to be our denominator in all of our F-scores. So we have 3 different hypotheses and 3 separate F values as a result. One for main effect A, one for main effect B, and one for the interaction A times B. So how we find F for the factor A is we take the mean squares for A, we divide it by the mean squares within treatment. We do the same kind of thing for B. We take the mean squares for B and divide it by the mean squares within treatment. And the interaction, and we take the mean squares, I keep saying that, for the interaction and divide it by the mean squares within treatment. These are 3 different F-scores that we're going to come up with. And here, this is where they'll be on our table. So using this fancy table, we can work it all out. So we're going to use the F distribution table right now just to see what it's like to evaluate whether or not our F statistic is significant. We're going to use the degrees of freedom for the numerator, which you've already figured out how to do in the last video, and the degrees of freedom for the denominator, which is basically the degrees of freedom within for the study, for each hypothesis and F value. We're going to find degrees of freedom for main effect A, main effect B, and the interaction. And the critical boundaries for each of these different hypotheses may not be the same. It's going to depend on how many rows and columns there are in the study. So here's an example. A psychologist used a 2x3 design to examine stereotype threat situations and gender with an N of 30 total. Results using alpha 0.05 were as followed. So A had an F statistic of 11.13, B 3.10, and the interaction was 7.45. We're going to use the F distribution table to determine whether the results were statistically significant. Now what we have next to our F labels are the degrees of freedom. So how did we get these degrees of freedom? Well, first of all, the first degree of freedom is what we figured out how to do in the last video. And the second degree of freedom here is the degrees of freedom within for this study. We had 30 people in the study. And if you remember, degrees of freedom within is N minus K. We had 6 different conditions. 30 minus 6 is 24. All right, so let's now look at degrees of freedom 1 and 24 to find out what is the critical value. So I'm circling first number 1, then 24, and I end up with a critical value right here of 4.26. So did our factor A exceed 4.26? Well, it definitely did. 11.13 is much more than 4.26. We're going to reject the null hypothesis. We reject the idea that there is no difference between the levels of factor A. We say there is a difference. And we reject it at the alpha 0.05 level. Let's try the next one. This one has a degrees of freedom of 2 and 24. So I'm going to circle 2, and I'm going to circle 24. And now our critical value is 3.40. Did we exceed that on the second one on factor B? Well, factor B was 3.10. It did not quite rise to that level. So in this case, we failed to reject the null hypothesis. Let's look at the interaction with degrees of freedom 2 and 24. It's going to be the same level of critical value that we had before, 3.40. and our F for the interaction of 7.45 is greater than our critical value. So in this case, we reject the null hypothesis. We say that there is a significant interaction. So as a reminder, the first one, we rejected the null hypothesis and we said the probability is less than 0.05. For factor B, we failed to reject the null hypothesis. And for the interaction, we reject the null hypothesis again. Let's try another one. An organizational psychologist uses a 2x2 design to examine levels of conscientiousness and levels of stress on error rates. So we have two different factors on error rates. This time we had an N of 36. And here were the results as follows. So in this case, because it's a 2x2 design, you'll notice that we have the same degrees of freedom for each one, right? So let's just go and look and see what is the critical value for degrees of freedom 1 and 32. So I'm going to circle my 1 and my 32, and I end up with a, it's way down here, 4.15 is our critical value. So in this case, we reject the null hypothesis for factor A because that's more than our critical value. We also reject it for factor B, but we failed to reject it for the interaction. So this is just some help in how you make a decision when you are using your F table for factor A, factor B, and the interaction. In the next video, we're going to walk through all the steps of hypothesis testing. I'll see you there.